the last problem I think in the regression that we are going to discuss is the outliers. And you have books that will tell you how to find outliers, how to determine outliers and treat them, but I find that those are mathematics people talking. Outliers could be one of the two things. Either it could be a mistake in your experiment, or it could be a real thing that you are missing, a phenomena. And so you cannot have, there is not a mathematical solution to this problem. You really have to look inside the system to find out why you got the measurement that you got. If you find a bug, that's fine, but you might discover that you really had missed some point that happens in that region of the operation. So just don't throw it away easily, because if it was a mistake, then fine, you can exclude it from the analysis and continue with the rest of it. But if it was some phenomena you missed, then obviously your model is incorrect and all the conclusions are incorrect and you have to redo all of them. So this is the line I'm saying here. The number of statistical tests have been proposed, and they are based upon certain assumptions which may or may not be valid, and so I'm not suggesting any mathematical method of finding outliers. Any value significantly away from the remaining observations should be investigated for errors, and in the neighborhood to find out should be conducted. So generally what happens is, if the outlier, there are some visual tests actually. Let me see if I have a graph here. There is a visual test here. Is that suppose you have a continuous graph and then just one point is over here. See this point, I wouldn't count this point, but let's say in the middle of this, one point is here. That is very likely to be an error, because the systems don't become that discontinuous in the middle. However, if there is a point here, then this is important to investigate why it is, because it is quite possible that the system starts a new operation zone from here. We don't know. Right? So just to do a mathematical test and say, well, this is an outlier and we are presenting this model, all you are saying is that we are presenting this model which applies to this range and we don't know for this range onwards. Alright, here the same thing. If you think that this is an outlier, then you are really modeling only this range and we don't know about what happens after this or above that. All right, let's see if we finish the other points. So, yeah, and so basically, this is the same thing we are saying, is that you may want to do some more experiment in that region to find out if this is just a error or a different region of operation. So now, so first thing that is important is to verify that the relationship is linear, because this will give you a very high R square. This particular model, for example, will give you very high R square, and that's all people do. They just measure the R square and they say it's good. But they forget that this is really, there is some kind of a phenomena here which is clearly visible to the eyes. Same thing here. This will give you a very high R square, because most of it is linear, except there is a region of operation which is being ignored. So now let's summarize with the common mistakes. And actually the first two we already said. First two were already said, that not verifying that the relationship is linear, and then relying on the automated results without visual verification. So there are lots of packages, and people just use the package and present the results, publish the results. They never have time to look at the results, look at these things in detail. And so same thing happened. For example, we were talking about my student doing some regression, and he did it, and basically I asked him to then look at the visual graphs, and we found something different. Yeah.
So A has a high R square as well, or it doesn't?
This one doesn't have a high R square. A actually could have high R square if this value is very high. See, what will happen is, these errors, if you fit a line here, then these errors are all small. Right? And this error would be 0 because, see what I mean? So it could have, depending upon the scale of this point. Good question. So now, attaching importance to numerical values of regression parameters, and then people will look at these numbers and say, well, this number is very small, this number is very large. That number has nothing, the numerical value has nothing to do with really the importance, because it depends upon what units you use. If you use memory in kilobytes, this is 0.001. If you use memory in bytes, it will be 1. And you use it in, what is happening here, megabyte. This is CPU time in seconds. Yeah, okay, so this is actually, I'm changing units on the left side. If it is in seconds, then it is 0.001. If I do it on the millisecond, then it is 1. And also if I change the unit of the y, of the x, then the numbers change. So the numbers have nothing to do with the numerical value of the numbers have nothing to do with their importance. Really, you have to look at the confidence interval, and here if it comes out 0, that means that is basically not important or not significant. All right. So that's the point, is that numerical values, don't look at the numerical values and say this is too small to be worrying about. Not specifying confidence interval for the parameters, most people don't, and they don't realize that this is as random as any of the means and other things. Not specifying the coefficient of determination, all right, that is the R square. Coefficient of determination, coefficient of correlation, confusing the coefficient of correlation. Coefficient of correlation is R and coefficient of determination is R squared. And so there's the relationship, people might misuse one for the other. R square is what gives you the percentage of variation. R gives you the correlation. Using highly correlated variables, so this was the multicollinearity problem. And people just put lots of parameters in the model without realizing that they are all related to each other. Using regression to predict far beyond the measured range. And that's a very common thing. People measure it for the last 5 years and predict for the next 50 years. Right? Using too many predictor variables, which is similar to multicollinearity. And actually, let's see, the list continues actually, but I have an even bigger list in the book, I suppose, but let's see. Subset giving the minimum R square is the best, but other subsets that are close may be used instead for practical or engineering reasons. For example, if the second best has only one variable compared to the 5 in the best, what is all this? K predictors. Okay, so this is related to K predictors, using too many predictor variables. Yeah, so basically what we said was that the solution for this was to run many subsets. And then among the subsets, you just don't want to take the best subset. Let me tell you how. I mean, we have a paper actually on video modeling. And the best model has, let's say, 10 parameters. All right? The second best, and maybe not even second best, let's say a model which had just one parameter was just only 1 or 2% bad. So now this is another art part. Which model would you suggest? That 15 parameter model, or that one which has one parameter but is only 1 or 2% bad? So that's the important thing, is we obviously recommended this simpler model, and we can live with that 1 or 2% error, increased error. At least in that situation for sure.
So that's a question then.
Yeah.
So when you judge between the different models, what do you use for the criteria?
So your criteria is still same. Criteria is still sum of squared errors left over, which is R squared. But the point is that the surface of R squared, if you were to look at the surface, is it flat? Which means, you could change around significantly without any difference, much difference, or is it very peaky? If it is very peaky, then yeah, you have to live with 15 parameters. But if it is flat surface, then you want to go to the simplest one. Does it make sense what I'm saying? No? Okay. So let's say I were to plot number of parameters and R square. Okay? If it was like this, then I am stuck with that particular value. But if this was more like this, then I would rather go for this. Let me just continue here. I would rather go for lower parameter number of parameters, simpler model, losing little bit. Again, how much you want to lose is not something that I can tell you. It's something that you use from the system's point of view. We are actually modeling here mobile video transmission over the wireless networks, and so we said, well, 1 or 2% error. Okay. All right. So that is what it is. Subset giving the minimum R square is the best, but other subsets that are close to may instead, for practical and engineering reasons, may be used. That's the point I was making. Okay. So you don't want to just do whatever the value gives you, but you can also see if there is equally good model. Equally good is again subjective, or not equally good. Or well, let's see. It's not equally good to be wrong word, but basically close to very good. Equally close model with less parameters. All right. Then second thing is measuring only a small subset of the complete range. So here the thing, you are measuring here, and then you are missing the behavior in other parts. Assuming that a good predictor is also a good control. That may not be the true. Predictor, if something gives you good prediction, does not mean that gives you good control. Control is totally different thing. So correlation means that you can predict. Control means you can change. So in the disk I/O versus CPU time regression, disk I/O can predict CPU time regression, but you cannot just change the disk I/O to change the CPU time. And we had given lots of other examples of correlation when we talked about correlation before. But all good predictor means is that it has a good correlation. That does not mean that it can be controlled. And it could be because you have a relationship with a third variable. So this is basically more about prediction and control. Prediction works both ways. If you can predict X from Y, you can predict Y from X. But control is the other way. You can control X from Y, but Y cannot control X. All right, everybody believes that? Okay. So that brings us to the end of this regression stuff. Too many predictors may make the model weak. This is one lesson you learned. There are several lessons you learned in this one, but first lesson is that having too many variables is not always good because those variables may be related. Then the categorical predictors, for those you really can use binary predictors. So that's another thing you learned, that if something has 4 values, then you want to have 3 binary variables to represent it. Then we learned about curvilinear regression, that you can somehow translate that into linear. And then more general thing is the transformation, where if you know the relationship between the standard deviations of the error and the y value, that relationship can be used to calculate what transformation is required. Then we talked about the outliers, and we said that rather than mathematically, try to find out from the system's point of view. And then common mistakes are, the very common mistake is no visual verification. Homework 15B. You have to fit a categorical variable model with some transformation.